Welcome back to some more geometry. Today, we're talking about proving triangles congruence. Now, as we stated in the last section, when it comes to proving triangles congruent, we always had to match up all three parts. We said, all right, we got two triangles that are congruent. That means we have to match up each individual part to their corresponding partner. That's the definition of congruent triangle, is that all six parts match up nicely to its corresponding friends. So we have this triangle has three angles and three sides, and they all had to match up. The three sides to the three angles. The three angles to the three angles, the three sides to the three sides. And that's what proved triangles congruent. Well, as we worked through this, we realized that it only takes three certain parts to prove these triangles congruent. Let's look at our first one. So our first one's called the side congruence. It says that if I can show that three sides of one triangle are congruent to the three corresponding sides of another triangle, then the triangle is congruent. So for example, this is how you see a mark. You'll see this side matches to that one, this one to this one, and the two bottom ones match to each other. So all right, the triangle is congruent. So we can say, hey, triangle ABC is congruent to triangle. And when you come, this is called the congruent statement. And the statement says the triangles are congruent to each other in this order. So ABC is congruent to DEF in that order, because we have to match up angle to angles as well as sides to sides. All right, so that's at the very end. You're going to be stating your congruent statement. This is the statement they're asking for. On this other one, let's look at this particular one. We know that IH is congruent to IJ, and HG is congruent to JG. So we say, all right, well, we got two sides to two sides. Where's the third side? Well, this one right here in the middle. Anytime triangles touch completely from tip to tip here, from end to end, all the way across, then that is the congruent side. Now, this one, for example, they're both kind of facing the same direction, facing upwards. So we'll say IG is congruent to IG, because they both share that same one side. So even though it's one side, it's almost treated like two different sides, because they're part of two different triangles. Now these two, this one side is congruent to itself. We call that reflexive property. But like, what happens if my shape is not as uniform as this one? Let's say they're kind of backwards. So if you look at this right here, this angle up here matches this angle down here. This one down here matches this one up here. So they're kind of backwards to each other. The smaller end of this triangle is over here. The smaller end of this triangle is going that way. So we say, all right, but it's still congruent. So A, B, C, D. So it still reflects a property, BD. We're talking about this side, but it's reflexive to its backwards version. So since let's talk about this triangle down here, ABD. So when we're talking about this side from B to D, we're talking about the bigger angle to the smaller angle to match up that side. So when we talk about the other one, it's kind of like you flip it around and say, oh, to match up BD down the bottom triangle, we have to match it up to DB of the top triangle. So this is still reflexive property, even though it's written backwards, but it still works out because we're talking about the same side, angle to angle here. So that's how reflexive property works. Anytime they're touching completely, whether they're backwards to each other or they're both kind of facing the same way, it's still reflexive regardless. All right, so that's side. Let's kind of do a little proofs to kind of support that. Now, our proofs will be done later in this section, in this chapter. We're going to do it. We have a whole package. But let's go ahead and get these down just to kind of help us remember it or see this. So this is called a float proof. A float proof kind of jots down some information and kind of leads to a new topic or kind of implies something else. It's where you kind of make some good assumptions that can really help you out. So let's start with the given information. So here we have QR is congruent to SR. So we're going to write in the first given. QR is congruent to SR. All right, we got that, and that's given information, so we write given underneath. So you write the statement inside the box, and you write the reason right outside. The next one says RT is bisects, that's shorthand of that, QS. So this array right here bisects this entire side right there. Okay, that's also given information. So let's start with this. So this already gives us a side. So we have something we need. We need 3 sides in this. So we got 1 side already. So I put a little S right there so remember. Now this is directly RT bisects QS doesn't help us, but it doesn't apply. Since RT did cut this whole side in half, it bisected, because again, bisect means 2 equal parts, we can then make the assumption QT has to be congruent to ST. So that's what this implies. It implies this next step. QT, wrong thing. QT is congruent to ST, like that. And that right there is definition of segment bisector. So we talked about this in the previous section about definition of segment bisector and angle bisector. When a ray or a segment splits a side or an angle in half, then you can imply that it creates 2 equal parts. All right, so here's our second side right there. So we need 1 more side. So we look at the picture right here. Kind of use it's okay to refer to the picture. All right, we got 1 side, 1 side, 1 side, 1 side. All right, we got sides matching up. We need 1 more. Well, this RT is shared by both sides. So we'll say RT is congruent to RT. And that's our reflexive property right there. So that's our third side. So then we could put all 3 of these together to ultimately have our final proven statement. Triangle QRT is congruent to triangle SRT. And the reason? Side, 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 because here's 1, 2, 3 sides. We get the sides matching up nicely. All right, so that's side, side, side in a nutshell. Our next one is side, angle, side. So this part right here, this is the important part. We're saying 2 sides and the included angle. So what it means by included angle is if I have kind of like an angle right here, I have the angle and the 2 sides right next to it, right there. This is what it means by included side. It has to be the 2 sides right next to it. And the angle has to be in between those 2 sides. So we're going to use this as our information. So I'm going to write some given information. We say NO is congruent to PO and MO is congruent to QO. So we're going to assume this is given to you. So say, all right, let's go ahead and mark what we know. We know NO to PO and then MO right there to QO right there. So we got the 2 sides that we're referring to. So we got this and this. We're missing the angle. So let's look at the problem. The only angle that can fit this particular problem is these 2 right here, because this is the only angle that's in between these 2 sides. We can't use N and we can't use M because they're outside the 2 angles, not between them. So we have to use this, but we can't call it angle O. No, because angle O is made up of 1, 2, 3, 4 different angles in that spot. So we refer to it by a 3-letter combination. To refer to this angle on the left-hand side particularly, we use angle NOM. That's congruent to its counterpart, so let's match it up. So N matches up to P, POQ. That's what you say, POQ. You always put where the angle's at, it's in the middle, and use the other 2 letters to kind of navigate the rays of that angle. And again, why are these 2 angles congruent, class? Why? Yeah, they're vertical angles. Vertical angles and reflective reflective sides are 2 things you can always assume. You can always assume those 2 things to be true. So vertical angles are congruent. So you can always assume those 2 things. All right, let's do a proof for this one to kind of support this right here. So we got these 2 triangles. They gave us the information that DE and FE are congruent, and EG right here bisects this entire angle right there. So this whole angle got cut in half. All right, so let's write that down. So DE congruent to FE. That's given, and then we know EG bisects angle DEF. That's also given information. All right, so we can imply something right here up to the next step. We know that this segment bisected this entire angle. Well, this angle got cut in half. It made 2 equal halves right there, creating 2 equal halves. We refer to them as angle DEG, and that's congruent to the other angle right here, FEG. Now, when it comes to matching them up, writing this down, you got to make sure they match up, okay? Figuratively, realistically, the goal is to say these D and F are the same, E is the same as that spot, and G is the same as that spot. So we got to make sure we match them up when we write them. All right, so we got a side right here, and then we got an angle. We're missing another side. So remember, anytime triangles touch, that side they touch completely is also congruent. So we'll say segment EG is congruent to segment EG. Right there. And the reason, again, reflexive property. And that's the other side we need. So now we got everything we need. So we can say the two triangles congruent by the side angle side congruence postulate. And there you go. That's side angle side. Now I have one more thing to cover. Now we already looked at this at the last section, saying that, hey, once we know two triangles are congruent, then we can say that all other parts are also congruent. So back in 5.2, we had to show all 6 parts were congruent, all 6 parts. But now that we know this SSS and SAS, we can say that once we show that 3 parts of one triangle match the 3 parts of the other one, the correct 3, then the triangle is congruent. And because the triangle is congruent, then the remaining 3 parts are congruent to their corresponding parts, or corresponding parts of those congruent triangles are congruent themselves. Or CPCT are equal, or you see it like this as well, just straight letters only. So let's kind of try this out. So here, the ultimate goal, the way you know you're dealing with one of these CPCTC problems is that when you're trying to prove either an angle or a segment is congruent, without having to prove the triangles. Like, whoa, you got to prove the triangles first. So if the final thing is to prove an angle or a segment, then that ultimately is a CPCTC problem. All right, so the goal here is to prove that angle LMN is congruent to LPN. That's the goal. Let's look at the given information we do know. They tell us that MN is congruent to PN, and LM is congruent to LP. So those individual points right there are congruent. So we're going to write this right here in the first step, because it's all given information. It's kind of given together. So we can write it together. There's no law that says it has to be separate. You can write it together. Now, looking at this, can I infer, can I go ahead and assume another thing is true? Well, I can't do an angle because the only thing we know is SSS and SAS, and this is the included angle, angle M and angle P. So I can't use that one because that's what we're trying to prove congruent. So we have to prove this triangle is congruent by SSS, looking at that reflexive property in the middle. LN is congruent to LN. Okay. That's congruent. So I got a side, and a side. So I'm done. My triangles are congruent for sure because of side, side property. So 9 times out of 10, you're done. But now that we know the triangle is congruent, we can go ahead and assume that these two angles are congruent by corresponding parts of congruent triangles are congruent, or CPCTC for short. All right, y'all. Hope that helps, and y'all have a great rest of your day. Bye.